Hi, everybody. Welcome back to asymptotics and perturbation methods. We're about to wrap up our discussion of the WKB method. I want to show an application of quantum theory today. This is in connection with so-called eigenvalue problems for differential equations. Very natural topic. So after we finish that, we'll have a few lectures to finish out the course on the method of multiple scales and related ideas. And I think we'll still have a few lectures left after that. There should still be some time. So maybe some applications to partial differential equations of the various things we've learned, or to difference equations where time is discrete or space is discrete. Yeah, we'll see. Anyway, it's really been fun so far. So let's finish strong. Just a few more to go. Okay, I'll share my screen with you here. Oops, that's the wrong screen. Excuse me. I'm a little flustered because my lunch was heating up in the microwave and it took a little too long, and I'm late. I'm late. All right, let me try this again. Share screen. Okay. All right, so applications of WKB to eigenvalue problems. You can read about this in section 10.5 of Bender and Orszag. So let me begin with something you may have run into in a differential equations course, a concept of a Sturm-Liouville problem. So this is the sort of thing that comes up when you're learning about eigenfunctions of the Laplacian, like maybe you've taken a course where they introduce basic ideas of partial differential equations, and you learn the technique of separation of variables. And often, like for the wave equation, the heat equation, Laplace's equation in one dimension, the Laplacian just becomes an ordinary second derivative operator in two dimensions, just taking the second derivative of a function. And when you look for eigenfunctions of that, you get sines and cosines. If you do the problem in cylindrical coordinates, you learn about Bessel functions. In spherical coordinates, you learn about, I don't know, what are those things called? Spherical harmonics, I guess. Anyway, so Sturm-Liouville theory is a theory that arose in the context of thinking about these kinds of questions coming out of partial differential equations. So anyway, here's a garden variety Sturm-Liouville problem. I've got a second derivative on my function y. This is a little bit not so typical in Sturm-Liouville, in elementary courses anyway. There's some function q of x, which we've run into before in our WKB problems. Except here it's being multiplied by this scalar e that's going to play the role of an eigenvalue for us. And so just to keep things simple, I'm going to focus on the case where the q has one sign. Let's suppose it's positive. Like if this were a constant positive quantity, then this really would just have sine and cosine solutions. Notice I'm constraining y to be 0 at both ends of an interval from 0 to pi. And so the question is to find a y that satisfies this differential equation and also satisfies these two boundary conditions. Now, for a typical e, this will not be possible. I mean, if you just pick your favorite real number e, you won't be able to satisfy the differential equation and the two boundary conditions for reasons I'll explain in a minute. It's only for certain e's that this problem will have a solution, and those e's are the so-called eigenvalues. So we expect to get in this theory, Sturm-Liouville theory, that you may have studied in your differential equations course, will tell us that there's a discrete set of these eigenvalues. We can number them with an integer n, 1, 2, 3, 4, and so on. So there's eigenvalues en corresponding eigenfunctions y sub n that then solve this problem. And the theory also tells us that the e's will get large as n gets large. So en will tend to infinity as n goes to infinity. Now, all of this becomes clear if you think about it visually in the right way. And so I want to give you the intuition that everybody has who works in this kind of topic. It's really helpful. So this is where I have not written things out ahead of time. Let's begin there. So the intuition for how to think about a problem like this is interpret y double prime as a kind of curvature of the function, the graph of y. I don't mean literally the curvature, because if you actually know what the curvature of a graph of y versus x is, it's a little more complicated than just the second derivative. So if you prefer, you could think of it as a measure of the concavity of the function. The idea being that if y double prime is positive, that looks like a parabola opening upward. If y double prime is negative, it looks sort of like a parabola opening downward. So interpret y double prime as the curvature or concavity of our graph of y of x. And then when you look at the equation, which tells us that y double prime is negative e times this positive quantity q of x all times y. Think about this visually, geometrically like this. If I draw my picture of, say, here's the region between x equals 0 and x equals pi. And let's suppose negative q of x, which is what we see appearing on the right-hand side of this equation. So suppose negative q of x is some kind of thing like this. Where 0 is up here somewhere, because q was assumed positive. So you've got some negative quantity there. And then when that multiplies, then we're also multiplying it by e. So if we think of e as positive, then when y is greater than 0, we will have y double prime less than 0. Right? In other words, when y is above the axis, y double prime is negative, which means it's going to look sort of parabolic opening downward. In other words, you're curving down when y is positive, and conversely, when y is below the axis, the x-axis, you're curving up. So what I'm saying is, you can kind of qualitatively imagine what the solutions will look like for positive e. If I were drawing, suppose I started here at showing y starting at 0. And imagine I start out going positively. And I'm consulting my function q as I go. So if my y starts out positive, then this tells me that I should expect y double prime to be negative. And so I'm going to start curving downward. And I'll do that. And then I'll actually at some point go through the axis, through the x-axis again. And so now I have to start curving upward. Right, so it's implying that you're going to get something that roughly looks sinusoidal. And this is going to keep happening. I shouldn't make it look like a sine wave. There's no telling it depends on the details of Q, exactly what it's going to look like. But still, it's going to be oscillating. And the thing is, it might, as it curves down, it might hit by the time it gets to pi that is at a place different from 0. In other words, it hasn't satisfied the boundary condition on the right side. And that may be because we chose the wrong E, right? This is why I'm saying that there are only certain E's for which you can solve this problem. Like in this case, you can see we didn't really curve enough. If this had just curved a little more, maybe it would have hit 0. So maybe if we increase E slightly, we could get something with a little bit more intense curving, and maybe it would look, I don't know, I'm just making this up, obviously, but maybe it would look sort of like this, bang, and then that one hits. So that was achieved by adjusting the E. That was an EN, and this was just some E that was too large, or maybe not large enough in this case. So anyway, I want to give you that intuition that you expect a discrete set of E's to work. And the reason it's discrete is because you're going to get a certain integer number of wiggles before you hit the boundary condition. So it really is kind of like what your high school physics teacher may have told you, that the reason, like a deep reason why things get quantized is because of standing waves, because of the conditions needed to put an integer number of wiggles, or actually a natural number of wiggles, in a standing wave. Okay, so I don't know if that worked for you or not, but anyway, this kind of thinking suggests that for large n, meaning we're going to have a lot of wiggles, we're going to expect that En will be large, causing a lot of curvature, thus provoking all the wiggles. Okay, so with all those bits of intuition in mind, this suggests a natural small parameter for our problem. I mean, at the moment, we don't have a small parameter, so why is it part of a perturbation theory course? Well, let's let epsilon squared be 1 over E. And let's think about the limit where that's small. So let's suppose that that's much less than 1. So the reason I'm defining it like that is because then my problem becomes translated into something we're used to. It becomes epsilon squared y double prime equals minus q of x times y. Right, just replacing the E by the 1 over epsilon squared. So now we recognize this because we've been studying this for the past 2 lectures. This is an example of what we call the Schrödinger class equation, not the Schrödinger equation. We're going to discuss that next, but this is of Schrödinger type. And so we have the WKB, lowest order solution for this that we discussed previously. I'll write it down in a second. So this is a Schrödinger equation. Okay, and as we saw then in the past 2 lectures, WKB approximation tells us that an asymptotic result in this case, in the limit as epsilon goes to 0, is y of x will be asymptotic to 1 over q of x to the 1/4 power times linear combination C1 sine function of 1 over epsilon, and then we had this indefinite integral 0 with an upper limit of x, square root of q of t dt. And then plus a similar term with the cosine. So 0 to x, square root of q of t dt. Close the big bracket. So we wrote that down in the past lecture or 2. And so that's an excellent approximation in the limit when epsilon is large. And we can use that to now start gaining information about eigenvalues, because if we take that as a form of the solution for these waves, then we can now impose the boundary conditions on it. So when y of 0 is 0 as one condition, what does that tell us? Well, notice that the integrals, I mean, y of 0 is 0. I have to plug in an upper limit x equals 0. So these integrals are both 0, right? I'm not doing any, I have no range of integration. It's just a point. So I have the sine of 0, which is 0, and the cosine of 0 is 1. So looking at that, in order to satisfy y of 0 is 0, there better not be any cosine term, right? So this implies that C2 has to equal 0 to satisfy that condition. Okay, and so now we've eliminated that. And so what about the other boundary condition? Well, y of pi equals 0 equals, according to this formula, I don't really need the q, that 1 over q to the 1/4, that's just some, when I evaluate it at pi, that just gives me some positive constant, which I can cancel out. The important point is that I can read off that C1 times the sine function of 1 over epsilon 0 to pi, because I'm plugging in x equals pi, square root q of t dt is 0. Now, if you say C1 equals 0, that's not very good, because that's what we would consider the trivial solution to our problem, right? That would, then the y would be identically 0, which does satisfy the boundary conditions and the differential equation, but it's not of great interest. The definition of an eigenfunction is something that's not identically 0. It has to be a non-zero solution to the problem. So that only leaves us to say that the sign of that bracketed term has to be 0, and the sine function is 0 at integer multiples of pi, right? Pi, 2 pi, 3 pi. So our condition is 1 over epsilon integral from 0 to pi square root of q of t dt is n pi, where n is 1, 2, 3, etc. We can't have negative n's because we know that the left-hand side is positive. So we get this quantized set of, we get this set of conditions, but now remember that epsilon was defined as, it has a relationship to E. E sub n, the eigenvalue that we're interested in, that would be 1 over epsilon squared. And according to this condition, then, that's going to be n squared pi squared all over this integral 0 to pi square root q of t dt, that whole thing squared. There. And so we expect this should work as n goes to infinity, because that was the regime where it's valid to be using WKB. That's a small epsilon regime. So that's a nifty calculation for the eigenvalues of this Sturm-Liouville problem. Maybe I'll put that in a box. Actually, let me drag it to where it's a little near the top of a page. Put it there. Okay. Cool. So any question about this argument? Okay, well, good. So then let's move on to the next example. When I said rather than a Schrodinger equation, we'll do the Schrodinger equation. This is an example in the book in Bender and Orsog that starts around, well, actually on page 497, they discuss what the Schrodinger equation is in quantum theory, which I don't really presume you know, although it would help if you've seen it. But and then they do their analysis of this two turning point problem on page 519 to 24. Okay, so here, you'll remember last time we talked about what happens when there's one turning point. And we did this interesting kind of elaborate calculation of using the WKB method on one side. Remember, a turning point is where this thing we're calling Q equals 0. And it's called that because of this classical picture from physics where you think of a potential well, like I'm drawing here, this function v of x. And I imagine a particle that is confined classically to roll around with some kinetic energy. It climbs up the wall of the potential till it's got no kinetic energy left. It's now all its energy is potential. It rolls back down, picks up speed, slows down again, gets to here, and it turns around when it reaches A or B, right? It rolls back and forth between A and B. And this is a really basic issue in physics. We use it as like for models of all kinds of vibrations, for chemical bonds, for all kinds of things. This picture of a particle in a potential well. So anyway, we got these classical turning points at A and B, but now we want to think about the quantum description of this. And so last time we discussed the idea that when you're in a regime where V is lower than E, we choose some level E that is like a candidate energy. Classically, a particle could have any energy inside a potential well. It's not quantized. You could have any continuous range of energy you want. But Schrödinger in the early 1920s came up with a way to explain why you have quantized atomic spectra, why you only see certain discrete spectral lines when you excite molecules to radiate or atoms. And so this was a partial differential equation explanation of where the quantization was coming from through these eigenvalue arguments. So what we talked about with the WKB with a single turning point was that on this side, which would be classically forbidden for the particle to be over here, we saw that there were sort of exponentially decaying solutions, or we could have exponentially growing ones as well in the WKB, but we felt that we should eliminate those by this boundary condition. We imposed a boundary condition that y is going to go to 0 out at infinity. So the kind of problem we're going to study looks like this. This is a Schrödinger equation again, where the role of the Q is now being played by this V of x minus E, the difference between V and this level E. And then that's all multiplying y. And we want to impose that y goes to 0 at infinity in both directions. And so we're going to have, using the intuition that we discussed earlier, we'll have something that looks sort of exponentially decaying on this side. It's going to start, our y is going to be oscillating in here. And when it goes through this turning point, then it's going to, we hope, exponentially decay on the other side. However, this is where it's tricky. When we did the turning point analysis, we only looked at one turning point, say this one. And we showed that it wasn't hard, wasn't so hard, to get something that exponentially decays out here, uses an Airy function to make the transition, then oscillates here. And that was as far as we got. But now here's the subtlety. We can do this problem both near A and near B. So we can impose that y will exponentially decay on this side, tunnel through this barrier, oscillate. But the thing is, the oscillations in the middle have to agree with what they would be if we imposed exponential decay on this side, and then tunnel through, and then oscillate coming from this direction. Do you see what I mean? The oscillations have to be compatible, coming both from A and B. And that is what causes a quantization condition. That's what determines the energy levels E. That was Schrödinger's basic idea, I think, to how you could get discrete energy levels out of a partial differential equation that he wrote down, which is essentially this one that we're writing down. So that's the intuition of how this is going to work. As I say, if you just pick E generically, just some typical E, the solution will blow up on either the right or the left side as x goes to infinity. because it will still contain some piece of that exponentially growing part of you remember the Airy function BI grows exponentially at infinity, unlike the AI, which decays. So typically you would have a little bit of BI. You have to really work to make sure you eliminate the BI terms on both ends. And doing that is what gives you the quantization. So as I say, Schrödinger's idea here is something like that solutions to this problem will exist and satisfy the two boundary conditions only if En is an eigenvalue. So that's what quantizes the energies. Okay, so as I've been trying to say, our strategy here is, I've written all this out because it's a lot of writing, that using the WKB approach, we're going to approximate the solution near A and B separately. We're going to then match the oscillations in that classically permissible region between A and B and watch what pops out of that. So let's first, maybe I should pause there. Do you want to ask anything about the strategy or anything else? You're with me? Okay. So let's look near B first. So visually, it's like I kept drawing that I'm going to impose 0 out here. I'll get my exponentially decaying solution. That's what I'm writing down first. Then I'm going to use the results from last time. I won't redo all the stuff with the Airy functions. We'll just take the known results for what happens on this side and then what happens on this side with the oscillations. So we'll take that as given. All right, so looking near x equals b first, we have this exponentially decaying solution, and it's got that characteristic constant over v minus e to the 1/4 power that we always see in WKB. Then, this was the important part of last lecture, we derived something, I don't think I use this terminology, connection formulas, but that's what they're called. The formulas that relate the exponential decay on one side to the sinusoidal behavior on the other side by way of the Airy connections. So the connection formulas that we derived last time, and if you want, you can find a good summary of them in the book in equation 10.4.13. The matching solution after you tunnel through is going to look like this. Hopefully that looks familiar. The things to be noticing are there was this slightly confusing factor of 2 that we discussed a little bit last time that came from a product of 2 square roots of 2. This characteristic 1/4 power is still there. Sine wave of something that looks like an indefinite integral, and I'm writing it going from x to b because x is the smaller of the numbers, x is less than b. I'm thinking of being in the region where x is between a and b, right, between the turning points. So in the permissible, the classically allowed region, we're getting oscillations that look like this. And then there's that interesting additive term of pi over 4 that you may remember from last time, which arose because of details about the asymptotics of Airy functions. You'll just have to go back and remind yourself, where did that pi over 4 come from? It's very important. So there it is. Okay, so that's my formula, and I'm going to need that so much, I'm going to put it in this big red box and call it Formula 1. Now, that's the way that the oscillations look from the standpoint of having tunneled through the point B. What about if you do the same thing near A? And so here, I'm going to, again, take care of my boundary condition at -infinity from the start by just saying I'm going to demand that y goes to 0 at -infinity. And so I get my exponentially decaying behavior over there when I'm for x's that are less than a. So in terms of the picture, I'm now way the heck over here, right? So I've got exponential decay of my y going this way. Those are x's less than a. Then I tunnel through to a and come into the oscillatory region. And I end up getting this connection formula, which looks very similar to what we wrote above. It's again got this 2, it's got this 1/4 power, It's got its own constant, C2, and it's got that same plus pi over 4 here. And here I'm going from A into a larger value, x, inside the permissible region, classically. So what's interesting now is I have two different expressions for the same thing. I have formula 1 and 2, which are both describing the oscillations of y between A and B. And those have to be the same expression, right? I mean, they overlap. They have to be the same function. And so that is going to give me a condition on E. Now, at this point, it requires a little bit of trigonometric cleverness. I feel like I want to make the screen or my image slightly smaller so you can see what's going on. You have to really look at these two versions, these two formulas. There's formula 1 and here's formula 2. I hope that's readable at that scale. They have to be the same. What I'm trying to say is they have to have the same x dependence. They're the same function of x. Well, do they have the same x dependence? They don't appear to when you just look at them because, well, this e minus v of x to the 1/4 power, that's the same. That's not causing any trouble. It's the fact that this integral goes from x to b, whereas this integral goes from a to x. So they look a little bit different. And what I want to do now is just a little bit of high school trigonometry to make them look the same. Do what it takes to make them look the same. That's really all I'm going to be doing here. So what do? Well, let me try to replace this integral from a to x by an integral that goes from x to b, and then put in whatever compensating terms I need to make that legitimate, to make that correct. So in other words, let me now do that at full size. Like I say, both 1 and 2 are valid in this region, x between a and b, so they have to agree. That's going to determine the eigenvalue E. So, of course, this is not giving us any information. That's the same in both. I have to somehow convert this integral to this. And I'm going to write it in this shorthand so you can keep your eye on the limits of integration. All right, so, I mean, this is not deep. This is just a little bit of tactical cleverness. Let's just stare at these pre-written expressions. In formula 1, let's see, it was in formula 2. Yeah, formula 2 had an expression that looks like this. Sine of 1 over epsilon, go from a to x, square root of something, plus pi over 4. That appears in equation 2. I want to make it look like what I see in equation 1, which was something that contained this kind of term. Excuse me, I see something going on in the chat. Let me see what that is. What about the constants? Yes, Maria, good question, right. There are C1 and C2. Those are adjustable. So yeah, of course, we have to get the constants to match up too. That doesn't really pose any difficulty. It's really the x dependence that takes a minute of thought. But yes, sure, the constants will match too. Good, right, that's right. Okay. So, but as I say, the x dependence is this in equation 2 and this in equation 1. And I can make equation 2 look like equation 1 by doing this little maneuver. So what have I done? I've kept the plus pi over 4. That's nothing's happening with that. But what I did was say that if I integrate from a to x, that's the same as integrating from a to b, and then subtract what I get by going from x to b. Right? That amounts to just going from a to x. So that's just a simple, additivity of what's happening in the integral. And then, since in my formula, I want to have a 1 over epsilon plus pi over 4 type expression, whereas this one has the wrong sign, right? This one has a negative 1 over epsilon and then plus a pi over 4. I need to add in a pi over 2 to convert this pi over 4 to something with the correct sign. Okay, in other words, if you just stare at this expression in the bottom line, this is the desirable thing that's appearing in equation 1. This was the compensating integral that I need. Notice it doesn't have any x dependence. It's just going from a to b. And this is the subtracting of the pi over 2 from this pi over 4 that makes me have a pi over 4 with the correct sign, after I put this negative sign out front here. So anyway, it's a bunch of little fussing. You may have to think about it for a minute. But the basic point is, I've now made the x dependence look the same in both WKB expressions at the cost of introducing this constant. This is some constant. I'm going to call it K. And that K is going to give me my quantization condition. So if I take this last expression here, this whole thing, and call it 3, then I just want to compare 1 and 3. And they will have the same, they'll be the same. I mean, so I'm ignoring the constants, the C1 and C2 for now. They have the same x dependence if I can ensure this condition. If I regard this sign of a sum as, something plus K, then I can expand trigonometrically to get a term that involves cosine of K and sine of K. Like, using a trig addition formula on the sine function. So I have a cosine K, a sine K, times the sine of the first term, the cosine of the first term. It's actually a sign of a difference, isn't it? It's this minus this. So I'm using the difference formula. But anyway, when you stare at this, you can see that in order for these to match, I need a sine to go with a sine. And so I'm going to need this whole cosine x dependent stuff, which cannot be matched over here. This has to be 0. This term has to be 0, which puts on the quantization condition that sine of K has to be 0. Then I have a hope of getting the x dependence to match. And then I will have to adjust the constants to make them match. I could tell you what the condition has to be. I don't think I wrote it down. Yeah, so the constants would have to satisfy, you can check C2 times -1 to the n plus 1 has to equal C1. I won't go into that. You can check that that's the condition you need on the constants. But the main thing is you need this sine of K to be 0 in order to get the x dependence to agree so that the oscillations are the same, whether you've tunneled through from the left or the right. And so what does that translate to? Sine of K equals 0. Again, excuse me. That tells me K is n pi. At the moment, I could imagine n could be any integer, 0, plus or minus 1, plus or minus 2. Soon I'm going to rule out some of those integers. But because by definition, what was K? K I wrote above was this thing, 1 over epsilon times the integral from a to b of that square root of q plus pi over 2. So writing everything out, K is this expression. And I'm now claiming it's n pi. So taking the pi over 2 to the other side of the equation, I get this, which is a kind of a nice result. That's telling me implicitly some condition on E. Given a potential V, I can read off the E's that will satisfy this for a given integer n. It's implicit, but still it's there. And now, of course, this side is positive. So the only allowed n's for this condition are n equals 1, 2, 3, and so on. And so rewriting that, it looks a little awkward to have n minus a half. The traditional way it's written is like this. that the eigen condition, if you want, is that the ENs are determined by this integral. 1 over epsilon times the integral of En minus V square root is n plus a half times pi. And here I've changed the definition of n slightly. The n is now starting at n equals 0. The point being that the lowest that this side can be is 1/2 pi. And so where do we expect that to work? There's actually two cases where you can think of it as being asymptotically valid. It works either if the epsilon is very small and you're keeping E fixed, you can get away with this formula, or you can think of it as the formula for high energy levels. For any fixed epsilon, if you take the number of wiggles going to infinity and the energies going to infinity, then this is also valid in that regime, either way. And Bender and Orsag discussed that a bit on page 521. So, it's funny, I may have written out too much today because that's all I have written out, but there were a few other things I wanted to say about this. So maybe I'll fill up some more time with that because I have a few more remarks. Do you want to ask anything about the argument up till this point? I realize maybe it was a little faster than usual.
Isn't epsilon defined in terms of En as well?
That was in the first problem.
Oh. That
was in the first problem. So if you'll recall back there, you're right. There we had that condition, right? That the epsilon was defined as 1 over, or epsilon squared was 1 over E. But in this problem, they're different. There's this epsilon squared sitting here. Epsilon squared in this problem is proportional to Planck's constant squared. I mean, that's one of the things I wanted to comment on now. If you took a physics class, how would they write this? They wouldn't write it like the way I did. So this epsilon is measuring the strength of quantum effects. Epsilon is proportional to Planck's constant. And this E is an energy level. So epsilon and E are conceptually separate here. But yeah, thanks. So they really are different. Right, so you can think of this, as I say, for epsilon fixed with E going to infinity, or you can think of it for E fixed with epsilon going to 0, which would be kind of like, and they call that the semi-classical limit, where you're thinking of the limit of Planck's constant going to 0, kind of. So anyway, this argument that we're making is a kind of semi-class. I don't know. Well, is this semi-classical? I'm not sure if this qualifies. I don't know enough physics to know if I use that word right. But let me write this down in quantum language for those of you who have seen quantum stuff before. Actually, maybe before I do that, I want to just show you one special case that's very famous, which is the so-called quantum harmonic oscillator. So I guess this would be example 3, which is, suppose we pick the V of X to be the simplest thing you could think of, just a quadratic potential. So I think, I'm not sure of the history. I think Schrodinger actually did solve this problem. He didn't do WKB, which is why his name is not on it. That came around the same time. I mean, Schrodinger's work is often dated as like 1923, 24, 25. WKB is all 1926. So they must have generalized a little bit of what Schrodinger had done. But anyway, in this case, E will equal V of X at 2 points, where X is plus or minus the square root of E. So those are our turning points. And let's consider the version of the problem where we'll just fix epsilon to be 1. So we're not thinking of small epsilon here. We're just going to fix epsilon to 1, and we're going to think about high energy levels. So lots of wiggles. Let's suppose n is very large. So we want to estimate the high energy levels for the quantum harmonic oscillator using our WKB. The reason I'm doing this is because this eigen condition here in the box is kind of implicit. The quantum harmonic oscillator has the advantage that I can explicitly do this integral, and I can then read off the eigenvalues. So that's kind of fun. So let's just do that exactly solvable case. Also, at the bottom of a potential well, it sort of typically looks like a harmonic oscillator that you'd expect a parabolic minimum generically. So this is always a useful case to be aware of. Anyway, in this case, the eigencondition or maybe I should call it the characteristic equation to be a little more consistent with linear algebra speak. The condition on the eigenvalues would be, well, so I go integral between the turning points, which are then minus square root of e and plus square root of e. And then I have to do the integral of my square root of e minus v, which here is e minus x squared dx. And that's supposed to be n plus a half pi. And the integral on the left I can do with a substitution. If I say u equals x over square root of e, then this becomes what? This is now e times the integral from -1 to 1, square root of 1 minus u squared. If I've done that right, du. So I skipped a step there, right? I'm using du times square root of e is dx. So I get 1 square root of e when I replace the dx, and I get another square root of e from pulling it out of this expression and also pulling it out of the, after I do x squared, that becomes e times u squared, that comes out. So anyway, this is correct, what I've written on the left. And this I can do, that's exactly integrable and gives you pi over 2. I mean, this is the area under a circle, right? This is the area of a semicircle, the unit semicircle. You could think of it that way. So pi over 2 times e. And so equating the two expressions, that is these two, the pi's cancel out, and you're left with e sub n equals 2 times n plus a half. Or if you want, you could write it as 2n plus 1. So n starts at 0. So that's a very nifty little formula. So the eigenvalues then for this quantum harmonic oscillator, the energy levels are exactly equally spaced. They just go up like integers. They go up like the odd numbers, actually. Pretty cool. Beautiful result. Now, we think that this is, I mean, I wrote it down. I said n equals 0, 1, 2. Actually, our argument was only for n much greater than 1. WKB tells us that this is valid for n much greater than 1. But actually, it turns out this is exact. I mean, it's actually exact for all n, as shown in quantum mechanics courses. So I'm not going to go through that analysis, but it's a kind of a convenient coincidence that the WKB is not just giving us a good approximation, but in this case, it's actually giving us the exact result. A sort of lucky accident. maybe I should not say but, let me say actually exact. So that's very nice. Now, so if you do take a quantum course and you want to compare it to what we're doing here, this is what the notation would be there. In physics, the way it's usually written, the notation would be this, that you have minus Planck's constant divided by 2 pi, so that's called h bar squared over 2m. The thing we've been calling y is always called psi, the wave function, psi double prime, plus the potential v of x times the psi wave function is E psi. So this thing is called the time-independent Schrodinger equation. In one dimension. And here m is the mass of a particle that we're thinking of being confined to the well. And as I say, h bar is Planck's constant h divided by 2 pi. Which turns out to often be a more convenient quantity than h itself. And so in those courses, you could show that, that the harmonic oscillator has allowed energies or energy levels, E sub n is n plus a half times h bar times a frequency omega. So you may be wondering, where's this omega coming from? I don't know, is this a recognizable formula? Did any of you take enough physics that you've seen this kind of formula? Yeah, I mean, the n plus a half is the very striking thing. So let me just try to dredge up my own physics memories. It's been a while. Actually, let me put that down here. So you may remember E equals h bar omega, or E equals h nu. That's Einstein's law in the photoelectric effect for energy for a contained, what? So that's energy carried by a photon that is associated with light wave of frequency nu or omega, depending how you write your frequencies. So that's, yeah, that's energy carried by a packet of light. But then in this quantum harmonic oscillator problem, you get this fascinating plus 1/2. I mean, you can see this 1/2 kind of can be traced back to the pi over 2, and we got the pi over 2 because we had 2 pi over 4s from the Airy functions, from the connection formulas. This 1/2 is a very interesting thing, I think, because this shows you that the lowest allowed energy is not 0. It's 1/2 h bar omega. This is what people call the 0-point energy. That a quantum particle cannot have 0 energy. The lowest allowed energy it could have is the 0-point energy, 1/2 h bar omega. Like, I guess nothing can ever be totally still. Maybe from some quantum, you could view it as some aspect of the uncertainty principle or something, right? If it were totally still, you'd know where it was and that it was motionless, and that's not allowed. You can't have that. So this 0-point energy is kind of popping out of our analysis here today. I didn't really say what the omega is, just for, since I'm filling up time here. Just as further reminders, all of this gets derived in quantum theory by you start with the time-dependent Schrodinger equation. Which looks like this. I h bar d capital psi dt is a Hamiltonian operator times psi, where the Hamiltonian, so the big psi is related to the psi that we've been writing by, this one is a function of both space and time. And it's got this space-dependent part, psi of x, and then an e to the minus I omega t. So we're looking for solutions of that type. That's the omega I'm talking about, this plane wave, or well, I guess it'd be plane wave if I said psi of x was e to the I kx. But I think this is what you plug in to the time-dependent Schrodinger equation. The h here is sort of operator notation for the second derivative operator, minus h bar squared over 2m, second derivative with respect to space, plus potential times psi. And so if you plug in this form for psi in here and in here, the time-dependent part goes away, and you just get the space, the time-independent Schrodinger equation that we wrote earlier. But anyway, that's where the omega is coming from. So, okay, anyway. So this is how our stuff connects a little bit to standard quantum theory. And it's kind of, I'm at the outer limits of what I know. I only took one semester. Or I think I did take a second semester, but I didn't get much out of that one. So, okay, so I'm actually prepared to stop early today. Unless you have any questions, we can adjourn. Do you want to bring anything up?
I didn't understand why the approximation that we found was valid for large energy levels, because when we originally derived the WKB approximation, the assumption was just on the parameter epsilon getting small. So so I guess I don't see why the WKB approximation is valid.
Yes.
Large energy levels. Does that question?
Yes. I think I didn't really say, did I? I think that's something I copied out of Bender and Orsog. You're referring to this remark.
That's right, yeah.
Right? Yeah, because all we know is that it should work for small epsilon with E fixed. That was the world we were operating in. But Bender and Orsog make this comment on page 521 that it can also apply even if epsilon is fixed. And it can be as large as 1. So why? Let's see now. Yeah, that's a fair question. I'm not sure. I mean, we could consult what they say, or maybe we could try to think about it. It's a good question. Yeah, why? So presumably the whole analysis is supposed to be valid for large E.
I mean, it seems like it's by analogy to the first example that we did, where E and epsilon were connected, and we Maria asked this question earlier also of if E and epsilon were still connected in this scenario, and
right, they probably are, and there probably is some analogy like that. So, but I'm not seeing instantly what to say about it.
I'm thinking of something like if you divide the entire equation by an E, and then you would have epsilon squared over E, and that should be something that should be small. So then you can either have epsilon small or E large. And then you'd have to deal with a V over E term. But if you look at x goes to infinity, then V over E should be like reasonable. I don't know, that's kind of what I was thinking about.
Yeah, well, I think we think of V as being order 1. I get, well, not necessarily, I suppose, right? Because if we do allow for very high E's, oh, I take it back. Right, V is allowed to get large as it goes out towards infinity. That's right. So I guess we can, interesting. So yeah, so your idea is rescale the whole equation by dividing everything through by E.
Yeah.
And then redefine the potential to be V of X over E. And then you've got a natural small quantity, epsilon squared over E. And you do the WKB for that problem. Right? That's interesting. So if I hear you, it's like you're saying you want to think of taking, let me not use that funny color. I was thinking that would be more visible than it is. Yeah, it's interesting. So we could look at a new epsilon tilde squared equals this over E.
Yeah, that's what you do in WKB in physics.
Oh, thank you, Andrea.
Yeah.
Is that right?
Yep.
You do that, and then do you define,
because epsilon squared would be like something that is I over H bar, and if you just said that epsilon goes to 0, you would lose the quantum effects because that's mean setting H bar to 0, which is just having a classical physics. Therefore, you need to have large E for this approximation to work.
Ah, very good. Because earlier when I said semi-classical is like saying H go to 0, that felt wrong. That felt like, yeah. So, but you're saying,
so that's why we need to rescale it by E, as Maria said. So you have an approximation that is valid for large E's.
This is great. So then we're doing the Q of X to be V of X minus E all over E. Something like that. Right, and then we're applying WKB to that problem. Good. That seems plausible. And anyway, you say that's how they teach it to you in physics. Nice.
Yeah.
Nice. Okay. Good. Excellent. I love it. Thank you for asking that great question then, Mark. And does that satisfy everyone? I think that's right. That seems right. Okay. Good. So maybe I'll actually, for future reference, I'm going to grab this and put it somewhere else. Let me cut that. So I could say, let me paste it here. Right. Okay. And so as we can see by rescaling, something like that. Yeah. Okay, nice. All right, thank you very much. And appreciate the help there at the end. That was interesting. So next time, I think before we turn to multiple scales, I do want to make some use of our knowledge of Airy functions, since we've been talking about them, before we forget what they are. There's a little problem in dynamical systems called delayed bifurcation, which is the phenomenon where instead of looking at a bifurcation with some parameter held fixed, you imagine sweeping the parameter at some rate. Like you could imagine doing an experiment on an analog computer where you're watching a dynamical system and you've got a knob and you're turning the knob and changing a parameter. And you watch the system go from one type of behavior to another as you turn the knob past a critical point. But if you turn it too fast, what can happen is that the system has a certain memory and it won't make the bifurcation where you will expect it to. you will have to turn the knob past the bifurcation point before the system realizes, sort of like Wile E. Coyote, who's run off the cliff, you know, in the Roadrunner cartoons. He's run off and he hasn't realized yet that he's in outer space or in space before he starts dropping. So it's something like that. There's a delay in when the bifurcation occurs if you sweep it at a certain rate. And so we'll calculate the delay between when the bifurcation actually occurs versus where it would occur if you had a static bifurcation. That delayed bifurcation analysis ends up using Airy functions and corner layers and some of the things we already know. And so I want to do that before we leave the world of Airy functions and go into multiple scales. So that's what's coming next time. Okay, I'll see you then.